What's up, guys? Today we're going to be talking about a convolutional neural net I built in Python with Tensorflow to classify heart rhythms based off 12-lead EKG data. I'm going to link in the description the data set I used and also the paper that I modeled my neural net off of if you guys want to check that out. I think it'd be really fun if anybody wants to try making their own neural net with this data set, see if they could get higher accuracy than I got. The accuracy that I was able to get was 85%. So I was able to get my neural net guessing the right heart rhythm 85% of the time. The code is only 130 lines long, so it's really not too long. But I would say in order to get the most out of this, I would recommend that you have a pretty good understanding of Python, a fair understanding of neural nets in general. If you don't, feel free to watch my last video, How AI Learns, in 10 minutes. And then I would also say that you should have some understanding of matrix convolution, but if you don't worry, I'll go over it. Okay, so here is our project right here. We only have one Python file, main.py, and then here we have our samples. I think there's around 10,000 or something. And then we have this diagnostics.xlsx2. What this has is that this has the true heart rhythm for each patient. It also has a bunch of other heart data on the patients. If you want to have your neural nets guess those, I would also say that that would be very cool. But I just had to guess the rhythm. And then here's the main.py file. Like I said before, 138 lines. So let's just get into it. To start with, import OS, import sys, import random, all pretty basic. TensorFlow is going to be the main machine learning library that we're going to be using for this. So import TensorFlow. And then I import Keras just so that I don't have to go tf.keras for everything. Import pandas, import matplotlib. And then after that, we have a couple globals up here. So just the name of the EKG folder and then what the diagnostics are. We just use pandas to read that. And then here we have our neural net, right? So to start with, when we build our neural net, we have to pass it a couple values. We pass it an input shape, which just tells it what shape to expect for the data that it will be receiving. For our inputs, our EKG samples are 4,999 samples of 12 leads where each specific lead has one value at any given point, right? So 4,999 by 12 by 1. We also have to tell the neural net how many conditions there are because at the end, it'll output a probability distribution for each one of the conditions and we'll pick whichever probability is highest, right? So we tell it 10 conditions. And then kernel size, dilation, and hidden units, right? Kernel size and dilations we'll come back to, but hidden units is just for that last hidden layer right here. We just give it how many units we're going to use, right? So to start with, we have a reshape layer right here. I always end up needing to reshape my values that I pass to my TensorFlow neural nets. It's always thrown on like one extra one or something because it'll error if you don't. Just because of how they expect the data. So that's always a little annoying, but yeah, I just added on one extra dimension here. So after the reshape layer, then we get to our first convolutional layer. So what is a convolutional layer? So to briefly explain convolutional layers are layers whose activations are not generated by multiplying the input against a weight, but are instead generated by convolving a filter against an input matrix. Right? So if you don't know anything about matrix convolution is pretty much just taking one smaller matrix, running it over a larger matrix, and at each point you get a score of how similar that filter is to that specific part of the matrix. I talk more about matrix convolution in my video, creating ASCII videos in Python. I'll also link that one in the description. Check it out if you want to know more. But pretty much a simple way to think about matrix convolution is you have one smaller matrix that you run over a bigger matrix, and at any given point, you get a number that's a measure of how similar that bigger matrix is at that point to that smaller matrix, right? So you can think about it like, imagine you have a matrix that's 3 by 3, and the middle column is all ones, right? So 1, 1, 1. And then you have a larger matrix that's a combination of vertical lines and horizontal lines. Because that smaller matrix has 1, 1, 1 down the middle, we can think about it like a vertical line. So if we were to run that smaller matrix over the image with vertical lines and horizontal lines, let's say there's nothing here, low score, nothing here, low score. there's a vertical line here. If there's a vertical line that lines up with those ones in the center, we will get a higher similarity score, right? And then we keep moving it over. In any place there's a vertical line, we'll get a higher similarity score, right? So that's matrix convolution. Very simply, very dumbed down, but that is the general idea of it, is that you have a smaller matrix that you move over a larger matrix to see how similar the larger matrix is at any point to the smaller matrix. How do convolutional neural nets use this? Why do we care? Why have you explained this 5 times, Daniel? Well, the reason why I'm being so thorough with it is the way that convolutional neural nets work is that those filters are learned by the convolutional neural net. What does that mean? That means that the matrices that the convolutional neural net chooses to run over the image are representative of features that it learns are important, right? So given the EKG example, the neural net might learn that a spike like this is very important and it means X condition. It will then create a filter that looks like this and run that over the image to see at any given point of the, I said image, but run it over the EKG data to see at any given point how similar the EKG data is to that spike. So that's what it's doing, and that's the way that it's generating its activations. So we have our first convolutional layer right here, and it has some arguments. One argument is dilations, one argument is kernel size, one argument is activation. Let's go through each one of those. So let's start with kernel size. Kernel size is going to be how many values are in our kernel. Here we have 3 by 3, so the kernel is going to be a 3 by 3 matrix. And I say kernel here, I was saying filters earlier. They're both the same, right? The kernel is that smaller matrix that we're going to run over the larger matrix to generate our activations. And here we choose a 3 by 3 kernel. So that means that the features that the neural net is looking for are going to be 3 by 3, right? So value here, value here, value here, value here, value here, right? So on. But then we use dilations to make that even bigger. Now, what are dilations? Dilations are a way to increase the size of the kernel without adding more values to the kernel. What does that mean? That pretty much just means you take your 3 by 3 matrix and you keep this value in the top corner, you keep this value in the top corner, you keep this value in the middle, right? That middle column stays in the middle. But then you blow it up to a larger size while just keeping zeros everywhere else. Why is this important? Why is this good? Well, sometimes you want to look at a larger part of the image without making that filter, the one that you're looking for, any more complex. To give an example, if the feature that my neural net is looking for is just a line like this, I don't need that line to have a bunch of values in the kernel, all right? I don't need to have a kernel that's 27 by 27 when this can be represented in 1, 2, 3, 4 points, right? So what do? Well, I have a small kernel that represents 1, 2, 3, 4 points, right? Maybe a 5 by 5 kernel, but then I blow it up using dilations so that it can look at a larger part of that image, because maybe in the image or in the EKG data, this line right here will take up 200 by 200 pixels, right? But I don't need my kernel to have 200 pixels because then a lot of it's just gonna be noise. So those are dilations, that's kernel size. Activation, here we pick rectified linear unit. If you don't know about activations, I would say watch my last video on how AI learns. But activations pretty much, what they do is they just add nonlinearity into the mix, because if you have a neural net that's just multiplication and summation, it'll only ever model linear functions. So you add the activation functions to introduce nonlinearity. Here we pick rectified linear unit. What rectified linear unit does is it sets all values that are negative to 0 and then keeps all positive values the same. And then we add a little bit of padding here. Padding, what it does is, remember how I said the matrix convolution is moving that kernel over the image? What padding allows you to do is it allows you to move that kernel a little over the edge of the image, right? So it adds some zeros onto the edge of the image so that you can put that kernel right on the edge right there, right? So we give it some padding. We have a batch normalization layer. So batch normalization, this is just a pretty standard thing to keep your values normalized. It's best in a neural net to make sure that your values are within a certain range so that the gradients can be more accurately calculated. That's the batch normalization layer. And then we have kind of the meat and potatoes of the neural net right here, which are alternating layers of convolutional and then max pooling. Convolutional, max pooling. So we talked about convolutional layers. We know that we're moving that kernel over to generate a score at any given point of how similar that part of the EKG data is to the filter that our neural net has learned. What are max pooling? Max pooling, what it does is it at certain points will only take the max value, right? At any given point when the filter moves over the EKG data, we're generating a number for how specific it is at that specific point, right? A lot of those numbers we don't care about. So what max pooling does is it throws away a lot of the numbers except for the max in a certain pool, right? So like I said before, convolutional, they have that filter that they're looking at and they're moving over. Max pooling has their own little window that they move over the activations from the matrix convolution, and it's only taking the max at any certain point. And this helps our neural net, one, limit the amount of numbers that it's processing, which just makes it computationally more efficient, but it also helps it focus on only the most important activations and throws away all those that we don't really care about or points that the similarity wasn't high enough. So we alternate. We go convolutional, max pooling, convolutional, max pooling. So something that you might be wondering is, why do we have so many convolutional layers? This is just so that we can look for deeper order features in the activations from previous convolutions. So the neural net can not only find features in the original EKG data, but it can actually find features in the activations from previous convolutions, right? And then when we have the max pooling, it's kind of like focusing a lens so that we only see the parts of the convolution that we care about, right? We are throwing away those useless parts that we didn't find a match or that were just kind of noise, and we're only focusing on the high similarity parts where the neural net was able to match a part of the EKG data to one of the filters that it learned. And then, after those two combinations of convolutional max pooling, we have a dropout layer. What a dropout layer does is it takes 20% of the activations here, 0.2, and it sets them to 0. Why would you want to do that? You're throwing away great data. Why would you want to do that? One of the main reasons that you do this is to prevent overtraining. If you don't know what overtraining is when a neural net stops learning the greater relationship between the data and the true answer and instead just starts memorizing, right? It just starts memorizing, oh, this one's this, this one's this, this one's this. And what happens is that it will perform very well on your training data, but then when you put it into the world with your testing data, or you use it in production, it won't be as accurate as it was on the training data because it pretty much just cheated and memorized the test. So what we do is we set 20% of those activations coming out of this layer to be 0. And what that will do is that then it adds a little bit of randomness because the neural net can't learn exactly what this answer is because 20% of it is gone. And that helps us get more accurate over time, right? Because we have to learn the general overarching idea without just memorizing each specific example. Then after that, we have another pattern of convolutional layer and max pooling. If you've noticed in these convolutional layers here, we bumped the dilations up by 2. So we multiply dilations by 2. And we do that again because dilations increase our kernel size. So we start out by looking at a kernel this big. So our filter is this big, moving over the image. But then we want to look for even larger things. So we bump the kernel up bigger and move it over our activations. And again, all the little things I did here, like picking the kernel size, picking the dilations, were done by trial and error. I ran it one way, I saw the accuracy. I ran it another way, saw the accuracy. And then after we have this final combination of convolutional layer and max pooling layer, we're going to have a flattened layer. And if you've been keeping up this whole time, you know that the activations coming out of each layer are matrices. What the flattened layer does is it takes these activations and it just turns them into a one-dimensional list of numbers. So no longer doing matrices, one-dimensional list. And this is because with convolutional neural nets, unless you want to generate an image or a matrix on the other side, at some point, if you want to do classification, you have to then connect it to a densely connected neural net, right? So you have all your convolutional layers, you have all the max pooling, all that jazz, and then at some point you flatten everything out and then you connect it up again to a dense layer where the nodes are just multiplying their inputs by weights and then summating all their connections and then performing the activation function, so on. So you have this flattened layer right here, which then connects it to this dense layer. This dense layer has 128 hidden units, and then it connects to the final output layer, which has 10 nodes, right? One node for each one of our conditions, and each node's activation at that point, because we're using the softmax activation, which, keeps all the activations to equal 1. Each node will have a, number 0 to 1 that is that node's probability of it being that condition, right? So each node here will represent a condition, and its activation at the final level when the neural net outputs will be how likely the neural net thinks that that EKG sample is that heart rhythm. That was the model as a whole, kind of going over it. I hope you guys understood. Let me know in the comments if you understood, if you like that. I'm working on explaining things simply. But then pretty much after that, all we have a progress bar. I think I copied this from Stack Overflow. We have a function that just kind of prints the shape of the EKG data. You can see how many samples there are. We have this that is used to convert the rhythm in characters to a number. So like I said before, at each point, at each node in that final output layer, it's going to have a probability of how the neural net thinks that condition is the one that's present in the EKG sample. So this just turns the heart rhythms from characters to a number. So if we look at our neural net, if it outputs 0, that means this. If it outputs 1, that means this. If it outputs 2, that means this, right? So then we have this function generate wide true here. This just reads through all the files and then turns the rhythms from characters into a number, returns that big stack of wide true. And then we have here our function to run batch. So a lot of you guys might be used to just seeing model.train. I can't remember why, but with this specific file, I decided to write my own batch function. So pretty much all this does is it just goes through, it gets what the neural net predicts for every single sample, and then of course it already has all the true values for each sample. So then we have our function here to run a batch. We pass it the index of wherever we're currently at in our training, right? So that we don't reuse old samples. We pass it a batch size. We pass it our EKG model. We pass it the Y true, so the true values for the batch that we're going to be looking at. EKG list, which are the samples that we're going to be looking at. And then an optimizer, right? Which is just going to apply the gradients. I can't remember why I wrote my own batch function for this. I know a lot of you guys might be used to just using model.train. But I wrote my own batch function with this. Pretty much all we're doing is we're writing the Y true and the Y predicted to a tensor array, right? We're going through for each sample, we're having the model predict what it thinks, and then we're writing that to Y true right here. We then calculate the loss after we're done with that batch by taking our Y true, comparing it to our Y predicted, and then we're also getting an accuracy just so that I can see how accurate the model is. After we have our loss, we generate the gradients, and gradients are just a fancy way of saying we generate which ways that we can move our weights to best minimize that loss. Again, if you haven't watched my last video, How AI Learns in 10 Minutes, that's a great watch if you don't understand this. And then we have our optimizer apply the gradients. And then here, we just have a function to run a whole epoch. An epoch is just training on all the data that we have. So this just runs through every single sample, updates the model, and prints out things as it goes. So yeah, that's pretty much it, guys. I kind of wanted to run through this, kind of talk through my thinking when building a convolutional neural net, maybe explain convolutional neural nets a little bit to somebody that doesn't understand them. Let me know what you thought of my explanation. I would really, really, really love it if anybody watching this who loves data science, who loves this sort of stuff, download the data set, give it a go yourself, build a neural net that's better than mine, let me know, even make a video about it, go ahead. But yeah, this one was really fun to do, only 138 lines, so pretty small, and yeah, hope you guys learned something. This is part of a series where I'm making a video every single day to just pass time when I'm looking for a software engineering job, let people know that I know how to code. So if you want to see more videos, if you have any ideas for other videos I do or want to check out my other videos, subscribe, leave a comment, and I'll see you guys tomorrow.